Okay, so on router 2, notice that we now establish our targeted LDP sessions. If we look at the show MPLS LDP neighbors, we're peered with both router 4 and router 5 as multi-point peers. So these are targeted hellos. Same verifications as we went through before. If we look at the show MPLS layer 2 transport, and we look at the virtual circuits, we should see that we have a virtual circuit going to router 5 and to router 4. Okay, circuit ID is 1234. This was based on the VPN identifier that I configured under the virtual forwarding instance, the VFI. If we look at the show L2 transport, show MPLS L2 transport VC detail, this shows the other options like what's the MTU, what's the label value, and then what is the local service instance or what's the local attachment circuit that we are bound to, which in this case is that interface, gig 1.20. Well, actually, no, that's towards the core. The attachment circuit would be under the show L2, is it L2 VPN VFI? Yes. Okay, so this says that the peers are up. A split horizon, yes, is enabled. Okay, that's the default. So it basically means when a frame comes in from router 4, we cannot bridge it back to router 5. If we then look at the show bridge domain, if everything works, we should now be learning the MAC addresses. So we're learning the MACs out our local ports, and then we're also learning them out the remote pseudo wires. The pseudo wires being the L2 VPN circuits that LDP established between them. So if we now look at this from a packet capture point of view, from again the data plane point of view, it's going to look the same as it did before, where we should have a 2-label stack, where the bottom label is the one that was now signaled via LDP, and then the top label is the one that's signaled by the CORS protocol, which in this case happens to be LDP as well. From the customer edge point of view, if we look at the show IP OSPF neighbors, we now should have a full mesh of adjacencies to the other devices. Okay, in this case, I did not add this interface as an attachment circuit. We're just bridging in here and then out these 3 directions. So from router 1, if we do a ping over to, let's say, router 8, so ping 8888, and let's just send 1 packet, we should see when it goes into the core, it's coming in first from the provider edge router as a 2-label stack. So we have number 25 on the transport label, we have number 26 on the VPN label, and then Ethernet is being directly encapsulated in MPLS. If we look at this from the transport network's point of view, so this is coming in on router 2, and if we show MPLS forwarding table, the first label, number 25, is talking about the transport label to the remote PE. The inner label, number 26, this is going to be the layer 2 VPN label that router 5 allocated to router 2. So we would see this in the reverse manner. So if we were to go over to router 5 and look at the same thing, the show MPLS forwarding table, if we look at number 26, this is the one that is on our local layer 2 circuit. And let's see, how can we see this identifier? Is to say the, let's see if we can match it based on the interface. Well, the interface is point to point. I believe we could just say detail here and look at all of the output. Well, actually, no, it doesn't even show you what interface it's going out. I think from this we need to look at the show L2, show MPLS L2 transport to figure out what the actual label stack is. Okay, so let's recap this config again. If we look at the show run, we have on the physical port level going to the customer, we have the service instance. Again, in this case, service instance is just saying all traffic. This means that if we had multiple VLANs, it looks like all the customer routers are plugged into an Ethernet switch that's trunking. So it'll do any-to-any VLAN transport. You can get a lot more granular than this. Again, you can say, as I receive the VLAN, I want to change it into a different one. As I receive the VLAN, I want to add VLAN tags or remove VLAN tags. That's part of that Ethernet virtual connection or the EVC configuration, same as what you would see on the Metro Ethernet switches. But in our case, we're keeping it pretty basic. We're saying all Ethernet traffic that comes in that port is part of service instance 1. Okay, then the service instance is called from the bridge domain. Bridge domain is saying, I'm going to take traffic as it comes in gig 2 on service instance 1. I'm going to bridge it out to this virtual forwarding instance. The VFI is the one that is calling the BGP signaling. So it's saying, with L2 VPN, I want you to advertise to your iBGP peers, and technically it could be eBGP as well. You could do like inner AS option B with this. So to the eBGP peers, to iBGP peers, advertise the route that is advertising what is my endpoint of the pseudo-wire tunnel, which in this case is basically your loopback plus the combination of the VPN identifier, which in this case was 1234. So if we were to configure this, let's say we have another interface that we want to use, and let me actually copy this out and I'll show another minor variation of what this would look like. Would be to say, okay, we have that one context, we have this bridge domain, and then we have the service instance. Okay, but I'm now going to change this so that we have multiple VPLSs. Let's say that we have one tunnel that's going to go between 8 and 9, and then the other one, the other one that is going between 1, 7, and 8. So we're going to have 1, 7, and 8. So it's coming out this way, and this way. And then we'll have one that goes from 9 over to 8 as well. Okay, so 8 and 9. And we'll say that this is going to be VLAN 89. This now means on router 5's physical interface, we're going to have 2 different service instances. One that's going to be for the 178 VPLS, one that's going to be for the 8 and 9 VPLS. And the way that we're going to categorize this is simply based on the VLAN tags. Okay, so on router 5, we're going to, and I probably have to delete the config because I don't think we can change the service instance while it's bound to the VFI. So we'll say on gig 2, no service, or let's see this, can I change it to encapsulation is untagged? Okay, it does allow that. So basically this is saying now match the native VLAN. On the other end, which is router 8 on the physical port is using this 10 network as the native VLAN, okay, because the main interface for Ethernet by default is untagged. But we can also configure sub-interfaces. So let's say we have interface gig2.89. The encapsulation is .1Q89. IP address 89008. Okay, now from router 5's point of view, we're going to match this based on a new service instance. So let's say that this is service instance number 89. And this is matching encapsulation .1Q 89. Okay, we're going to do the same thing on the other side. So on router 2, we'll say that we have on interface gig 3, we have service instance 89 that says encapsulation is .1Q 89. Okay, on the other end of router 9, we're going to have interface gig 2.89. And technically, the numbers don't have to match between each other because now with the service instance, the VLAN number is locally significant. I could use VLAN 1234 between router 9 and router 2 and then translate that to VLAN 89 on the other side by popping the tags and then rewriting the numbers. So on router 9, we'll say encap.1Q89, IP address 89009. Okay, and let's do a ping to 89008, and we'll leave this going while we're building the rest of the config. Okay, so we already have the service instances, like on router 2, if we show run on port gig 3. The same is, and actually I need to remove that one. Okay, you cannot have default plus another encapsulation at the same time. It actually shouldn't let you do this. It should give a parser error because default doesn't mean untagged. Default means everything. and it's processed top down. So if this one is listed before service instance 89, then 89 never gets hit. It's kind of like an access list. This is just saying permit any, and then anything below that is not going to get matched. Okay, so I need to delete instance number 1 here. Okay, same should be true on router 5. If we show run interface gig 3, no, gig 2. Okay, we have the service instance, and again, this one needs to, actually that one can stay. Okay, now we're going to match them in a new bridge domain and a new VFI. So we're going to say, let me put this in a new window. We'll say that this is going to be VPLS 2, where VPLS 2 is going to be, or let's say 200. Okay, just so we have a new number. 200, VPN ID is going to be 200. We're still using BGP for signaling because we already have the peerings configured. So this is going to go on router 2. And that should have said service instance, this one, service instance 89. Okay, wrong numbers there. And then on router 5, the different port number. Okay, now we already have the targeted LDP session that's going to router 2. The difference now should be is that we're going to generate a new BGP advertisement that's talking about this separate VPLS based on the new VPN identifier, which is essentially the route distinguisher. So if we look at the route reflector and look at the show BGP, L2 VPN, VPLS all, we now have 2 separate sets of routes, where this is VPLS 1, this is VPLS 2, and then the same as like an L3 VPN, they're like in different VRFs where they're not exchanging traffic between each other. So now if we look at router 9, this has reachability to 8. And in this case, they're actually running OSPF because they're running OSPF on all interfaces. But the only thing that we needed to do on the provider edge routers was just to bind a new service instance to the physical port and then map that to a new set of virtual circuits based on the BGP Autodiscovery. And this is really the reason why you would want to use the service instance as opposed to using the legacy syntax, is that if you want to come back later and add some sort of new service, you don't have to give them a new physical interface. Like give the customer a new physical interface, you can split it into different logical services simply based on the VLAN tag that is coming in that port. So you could have, for example, like a VPLS that's for internet access, and you could have a VPLS that's for private WAN. You could have one that's for intranet access, like, or extranet access, I should say, like for central services. Same type of logic as we looked at in L3 VPN. Okay, so again, on the route reflector, if we look at the show run section BGP, this is not directly related to the provider edge config. It's just that router 6 is accepting all the routes in from everybody and it's reflecting them back out. It does not do route target filtering, just like in L3 VPN. So when we add this statement here that they are a route reflector client, this says accept all routes and then advertise all routes back on. We would have the same exact effect here if we had peered directly from 2 to 4, 2 to 5, and then 4 to 5. But since we're trying to do auto discovery, peering directly between them kind of defeats the purpose of the auto discovery to begin with. In more practical cases, you would have a route reflector infrastructure in the middle. Okay, then on the PE routers, we had those 3 constructs, which were the service instance at the physical port, the virtual forwarding instance, which is calling the remote neighbors. In this case, they were discovered by BGP. And then the bridge domain that's combining the 2 of these together. So when we look at, again, the capture from the data plane, we should see that when we look at the source of traffic that is coming in from, and let's go back to the main, that I need to restart. Okay, let me restart a new capture. And let's say IP.source is equal to 2222. So we see these LDP messages. This is where we're exchanging the label values for the actual circuits. So let's say, for example, that on router 2, one of the attachment circuits goes down and then comes back up. We would have to send a new label mapping message to them. Okay, no shut. And then we can see now, here's the TCP exchange. Okay, this is them actually advertising the label numbers, which would be like this. So somewhere here in the payload, it's basically going to say whatever the label number is that we want to use for that individual pseudo wire. But the point here being is that this is not BGP that's doing that signaling. This is LDP that is doing that signaling. The other variation of this config is to do BGP for everything, which is a little bit more involved. Okay, in the case of the documentation, where you would find this is, if we go to the main doc page, let's go to Products iOS. iOS XE S, 3S. Then under our config guides, under MPLS, L2 VPN, and then this is VPLS Autodiscovery BGP based. Okay, so if we look at the config example, this is the legacy syntax, but it's basically the same logic as the next one. Okay, you'll notice that it shows you both of these for all the examples, what the Autodiscovery was, and then now using the associated L2 VPN protocol-based CLI. This is the one that's standard between all of the OSs now. So we created the VFI, gave it the identifier. This is where it's getting the route distinguisher from, and then it's saying we're going to use LDP to discover the neighbors. Then we had some sort of peering design that we have L2 VPN enabled. Then we have the physical port that is going to be, I don't know if they actually show that here. This just shows just the BGP related config. You would still need to look at there's a separate document that's just configuring VPLS. Configure virtual private LAN services.